Othek will fill up for any gaps, questions that I can't answer. This lecture is about the Nobel Prize in Physics for 2020, about half of it, because one half is divided into 2/4 given to Getz and Genzel. Am I right, Othek? Do I pronounce their names right?
Yes. Getz is actually a Jewish name from North Africa, and Reinhard Genzel is very non-Jewish. He's German, and they did the mapping of the center of our galaxy and inferred the black hole that's in the middle by the orbits of what they call S stars around the center of the galaxy. If anyone wants next week or a week after that, during the semester, maybe towards the Nobel award date, which is December 10th, would want to present their work, feel free to do that as well.
You muted me, apparently. Okay, so the prize was granted to Sir Roger Penrose, for the discovery that black hole formation is a robust prediction of general theory of relativity. So very soon I'll review a bit of the historical context, but before that I'll make a short review of black holes, spherical symmetrical black holes in general relativity. I don't know if you're all familiar with Einstein's field equations, which appear at the first row here, but in general relativity, the curvature of space-time is generated by the presence of energy and mass. So the right-hand side of the equation, you can see T mu nu, which is the stress energy tensor, which encompasses both matter and energy and momentum in the space. And on the right-hand and the left-hand side, you can see Ricci tensor, which is a measure of the curvature of space-time. And the metric, Ricci scalar, like the R without the indices, is the trace of the Ricci tensor. And the metric, which is G mu nu, which describes the distances between infinitesimal points in space-time, infinitesimal events, infinitesimal. If you assume that space-time is empty, it means the right-hand side of the equations is equals to 0, and then there are solutions for the left-hand side, given that assumption. The spherical symmetrical solution was given by Schwarzschild in 1916, a year after Einstein published his theory of general relativity, and is given by this metric. So, as one can see, it's spherical symmetric, like the dependence on the angles is summarized in the last term, which is the familiar flat space r square d theta square plus r square sinus theta d phi square, like the polar and azimuthal angles. While there is a curvature in the radial distance and the time that depends on the distance from the origin of the coordinate frame, depends on the relations between this to a Schwarzschild radius. Schwarzschild radius given in the next row, and actually can be derived from Newtonian classical mechanics assumptions. Is the radius that a mass under this in a volume that is less than this radius turns into a black hole. What does it mean, a black hole? The classical meaning of things is just like a very massive body that light can escape, the escape velocity of objects from this massive star or planet or whatever is bigger than the speed of light. In the more general relativity sense, it means the event horizon is a point in space in a given distance from the origin, which from that point you can't return to the outside world. You're basically, and you can't be static, you always converge to the singularity. Now, if you look at this metric, under dr square term, you got in the denominator, the term converges if r equals the Schwarzschild radius, like the denominator is 0 and the term converges. And also the general term converges when r equals 0, aka you're at the origin. Not aka, meaning that you're at the origin. We'll soon show that the divergence in the Schwarzschild radius is a mathematical divergence, which depends only on the choosing of coordinates, while the divergence at the singularity at the origin is a physical divergence. If you calculate the Ricci scalar at this point, which is a measure of the curvature of space-time, you'll get infinite value. I just re-emphasize that it means this is a spherical symmetric solution. Ofik, anything to add on this, or any questions so far? Okay.
Just that the theorem that says that if you try to squeeze matter into a volume or into a radius smaller than the Schwarzschild radius, then it collapses to a black hole, is what's called the hoop conjecture. Historically, people thought of it in a axis symmetric spacetime, which has fewer dimensions, so it's easier to do. So they thought of a big cylinder, and when the cylinder gets squeezed under this radius, so you can kind of imagine a hoop, chishuk in Hebrew, around it, then it would collapse to a black hole. So it's conjectured to be the densest you can get a particular mass to be. That's it.
Okay, I'll forgot to say before that this metric is also applies to non-black hole objects after outside of this, like the sun outside of the sun. This metric applies in close approximation. Like the sun is not spherical symmetric and it's rotating, but first approximation like Mercury perihelion and other GR phenomena were first calculated using that metric. Okay, there was an historical debate whether black holes can form at all, or are just like neat and aesthetic mathematical solution to the field equations. Some footnotes of this debate: Robert Oppenheimer and his student Hartland Snyder made a calculation, which we'll review shortly later, about cloud of gas or matter that is spherical symmetric, and it collapses and forms a black hole after the matter encompasses less than its event horizon, gets a critical density. Einstein actually doubted it on the same year in 1939, and Evgeny Lifshitz, very well known, and Isaac Khalatnikov, please correct me if I'm wrong if anyone knows, revisited Oppenheimer and Snyder's calculation and claimed it does not represent a physical reality. Like, you don't have spherical symmetric arrays in the universe. That was in 1963. But in the same year, there was the first evidence, observational evidence of a supermassive black hole, like a mass, a very big mass, I can check for the exact numbers, was observed. And if it would prove to be a star this massive cannot be stable because of the internal forces. And also a solution for a rotating black hole was given in the same year by Kerr, which we'll repeat to later. It retained some of the symmetry, like cylindrical symmetry, but not the spherical symmetry. And also, and it showed that singularities can form under more general symmetries, in more general cases. So after all, we're talking about
2 points on the history. If you go back, first about why there was even this debate, which to us now it seems obvious that there are black holes. The Einstein's equation, of course, is a highly nonlinear partial differential equation. And those have very weird behaviors and very weird solutions. And it's sometimes difficult to mathematically define or prove theorems about what those solutions may or may not be. The closest analogy is hydrodynamics. The Navier-Stokes equations in hydrodynamics, which govern fluids, that's also a nonlinear partial differential equation. And to this day, we don't actually know and cannot prove whether the equation is what's called in differential equations, whether it's well-defined, whether it has stable, well-defined solutions that come from initial conditions, or maybe there are multiple solutions, maybe there are irregularities, chaos can arise in these systems. A lot of things can happen in hydrodynamics. Many of those problems or singularities that can arise in hydrodynamics, even from a non-singular initial condition, that is, you can create a flow which would cause it to evolve into a singularity, into some shock waves, even if it started rather calm. Some of the effects that come in there can be things like viscosity or turbulence or other effects, which sometimes create singularities where you wouldn't expect them, and sometimes smooth out singularities and avoid singularities even when you might have feared that there might be one. And that's still an open question in hydrodynamics. There's actually a $1 million award open to anyone who proves an answer to the question. It's one of the longest standing open questions in mathematics. And general relativity, the Einstein equation, has a very similar form. It's a field equation very similarly. It's nonlinear, and it also deals with the question of starting from some initial conditions of the field and evolving it to see if singularity, if a black hole arises. So that's one of the reasons that nobody really knows all the answers. It's an open question still, and why different answers were given by different people. Many of them come from the field of hydrodynamics. So this Yevgeny Lifshitz, you might know him from the Landau-Lifshitz book series, in dealing, among other things, in field theory and hydrodynamics. The second point is about this 1963 observation of a supermassive black hole. The word observation is always problematic when one discusses black holes, because of course we cannot actually see them. They're black. They emit no electromagnetic radiation that we can easily see. What was actually observed in this case was what's now known as a quasar, which is an acronym for quasi-stellar object, a very, very intensive source of radiation, which can equal in its luminosity and its power an entire galaxy, but is very, very confined to a small space, something like smaller than the solar system or on the order of the solar system. And it was explained in those years that the only way you can eject so much energy, so much luminosity from such a small volume in space is if you have something that's as compact as a supermassive black hole. So huge mass, very, very dense, and the matter accreting onto this black hole would get very, very hot, would release a lot of energy, the gravitational energy from falling into the black hole, and that's really the energy that's being emitted and the great, great power that we see. So supermassive black holes were proposed as an engine for these quasars, and it was a quasar that was observed. Okay, that's what I had on the historical side.
Okay. Anyway, we're talking about Roger Penrose, and all these things led to the search for more exact and realistic process which describes similar process, a collapse process, more realistic description of the collapse process that Oppenheimer and Snyder gave kind of, can say, a toy example in today's terms, in retrospect. So first we'll review Penrose diagrams, which are essential to describe a space-time structure in complicated metrics. And then we'll shortly review the singularity theorems that Penrose was granted the prize for. So if we will take a flat space-time given by the following metric, which some of you or all of you recognize as special relativity metric in the absence of matter and curvature. Basically, dr square minus the angular part is like dt. Also, of course, the speed of light is 1, as is conventional in general relativity. And I'm not sure if I use the general relativity. How do you call this? Plus minus 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 or minus plus plus plus.
The metric sign convention. You don't. You use the particle convention because your time is positive.
My time is positive.
But that's fine.
So
we're all negative people.
So anyone who is not familiar with what I just said, in general relativists use a metric which the signs are switched, like the time dt squared comes with a minus sign and the spatial part comes with a plus sign. And the particle physicists use the notation I just used. We'll ignore the angular term in the next slides and just refer to the radial term and its relations to time. I mentioned before, okay, sorry. We have this we switch the coordinates to right-like coordinates, which is u is like t minus r and v is t plus r. And then the metric gets the following form, which doesn't mean a lot. But if you look at the diagram to the right, v is constant. We have the direction where v is constant and the direction where u is constant. And basically infinite time, like infinite future, is given in the upper side of the diagram. Infinite past, like if you go back to the past, is given in the bottom side of the diagram. And infinite space is given as you go to r equals infinity. And the light cone remains the same. But this diagram is not very informative, as still like the infinites are not given in a compact diagram. So we do another coordinate transformation, which is given here. And we define a psi and zeta as follows. And in this case, you can actually may have needed a better figure for this, but all the infinite time, like if you would see a radial constant, just a minute, radial constant, I'll look for a diagram, just a second. And Penrose diagram. Just want to see here. Okay. Copy image. Let's just do it shortly. Ignore the left-hand side. This diagram describes one-dimensional space instead of radial symmetric. So just refer to the right-hand side of this diamond, like what you see in the previous diagram. And all the lines you see are like a constant, all the vertical lines, close to vertical lines, are all like hyperbolas, are constant time word lines, and all the all the horizontal are constant time, and all the vertical hyperbolas are constant space word lines. So if you if you're in some point in space and you don't move, this diagram converges to the same point in the diagram. Like all the infinite future converge to the vertex at the top of the diagram, and all the infinite past converge to the vertex at the bottom of the diagram, and all the infinite space-time converge to the right-hand side of the diagram. Well, all light rays are going from either coming from the bottom right or going to the top right. Ofek, anything else to maybe more explanation or intuitive?
Sure, if you can just make the diagram a bit bigger. The important thing to see here, that's a good big diagram. Like you said, the hyperbolic lines which go from left to right basically cover all of space-time at a particular point in time. So they all start at distant infinitely far r or infinitely far space. They go back to infinitely far space. They cover all the space in between through the point 0, which is the origin of, or the center of the diagram. At time equals 0, it's just this flat axis, the flat horizontal axis. As time progresses, we can imagine taking time slices. That's what they're actually called in the field. Time slices of space-time, which is just freezing all of space at increasing points of time. So each of these curves that goes from left to right is a time slice. On the contrary, if you keep your position fixed and only increase time, you get the lines going from the bottom, which is infinite past, to the top, which is infinite future, time like infinity in the future. And those are called timelines or world lines, because if you're a particle or a person or an object, you must follow, and you stand in place, then you will follow one of these lines. And in fact, you can change your frame of reference in a special relativity sense, so that you're always fixed, for example, in the origin or fixed in any particular coordinate space, coordinate point r, and then you're just moving forward in time. The trick about the diagram is twofold. One is that the straight lines in the diagram are actually the diagonal lines, going at 45 degrees upper left or upper right. That is forward or up in time, and either left or right, which is higher r or lower r. And those are photon trajectories or light trajectories, null geodesics. The null trajectories are diagonal, and so the angles are the same. You see, even if we fold all the space and the time lines in this diagram, the angles are still the same between them. That's what conformal means. We do a manipulation of the geometry, but angles are still the same at every point. And of course, all of these light trajectories, they're the only lines that don't end at time like infinity or space-time infinity. They end on this diagonal side of the diamond, which is the edge of space-time, and that's basically representing the radiation going off to infinity, or the lower part, radiation coming in from infinity. We would typically assume that is 0, because we don't expect anything to fall into our space-time from anywhere. But things can go outside. And this diagram, because it preserves angles, that is, it's immediate to see where the 45-degree angle lines are, you can always tell whether 2 points are causally connected or not. If a point can be connected to a lower point in earlier time using a trajectory which is contained within a light cone, then they're causally connected. And if not, then they're not. So we paid the price of bending the representation of time and space, but we gained compactifying all of space-time, which is infinite, into a finite diamond. So it appears finite both in space and in time. It's compact in both space and time. And we preserved the light cone structure or the causal structure so we can see causality and causation and connectivity between different points. So this is the pen often called the causal diagram. It shows the causal structure of space-time.
Okay, we'll go from here. So this is the case for flat space-time. Now we'll see, now for a black hole, or a Schwarzschild black hole, we don't have the time now and didn't have the time to prepare it, but you can do a more complicated coordinate transformation, and which cancels the singularity, which I mentioned before, in the Schwarzschild radius. So before the conformal transformation, you get the top diagram, which has 4 regions. One is like our universe, outside of the black hole, and 3 is inside the black hole. Like the diagonal line is the event horizon. Event horizon is, as I mentioned before, is like the boundary of the black hole. While you have 2 and 4, which are more peculiar. 4 is the opposite of a black hole. It's a theorized white hole, which is an object that how to call it, like extracts matter instead of attracts it, matter and energy. And 2 is another universe. That's how it's like an asymptotically, not asymptotic, analytical, what's the term in English?
Continuation. Continuation.
Continuation of our space, which is another space. It was first theorized by Einstein. It's called the Einstein-Rosen bridge. If anyone is, actually, it's a very popular term in sci-fi shows and films these days. But the case of when we do a conformal transformation on this, like we have the new U and V that you see in the equation above. If you do a similar transformation to the one we've done before, you achieve this Penrose diagram, which you can either, if you're in region 1, you can either escape from the black hole or reach its singularity on the region 3, which is space-like singularity. Like it's a constant time and it's a given point in space, like at infinity. Ofek?
So first of all, about regions 2 and 4, you can see by construction of the diagram that if you live in the universe in region 1, you can never ever send any information or particle or anything into region 2 or 4, because the boundary between you is at a 45-degree angle. So it's outside of your causal future. 2 is outside of your causal past as well, as long as you're outside the black hole. So region 2 of the universe is, for all intents and purposes, not part of your causal universe. If you do live in region 1, then your future can be one of 3 options. You can transform yourself into pure energy and ride on a light ray outwards to the right and up side to I+, so to sky plus, to the future null infinity, the future light-like radiation infinity. So you spend your eternity going outwards, both in space and in time. You can live your life in the universe on a regular world line, which is confined to be in the diamond and at I+ future time like infinity. So just stay in the universe forever until the universe ends or whatever happens to it. Or you can go left, cross an event horizon, left and up, cross an event horizon, enter region 3, at which point you can never go back out, because that would require crossing a 45-degree angle line, which you cannot do. And because you have to always move forward in time, you'll be moving up in this diagram, in this causal diagram, until you eventually reach the squiggly line, which is the real singularity, the physical singularity, the curvature singularity at the center of the black hole. At which point, no one really knows what will happen.
Okay. Now, if we go back to Oppenheimer and Snyder's analysis, we can assume a sphere of matter, which is described like the shock wave that is listed here. Like all of the matter is like in a thin sphere. If you're inside it, you see a flat space-time. If you're outside of it, you see a Schwarzschild metric. And the sphere, because of gravitational forces, it collapses to form a black hole, but it has to be completely spherical symmetric. And we can watch the Penrose diagram of it on the bottom half of the page. So we have like the emergent, we have like the how to call it, the cut line, like the which is called event horizon. So before the black hole, and we have the shock wave. The shock wave is like given by the line with the arrows. And as time progresses, the sphere converges, and at a certain point, it is smaller than its Schwarzschild radius. This point is where the two lines cross. But if you are like in the region before, like close to the center, like you're inside this sphere, even before, if you go down from the point of the black hole formation, you still cannot escape the black hole. If you are like close to the center, but not, but before it in time, like down in the diagram. Because in order to escape it, you have to move past 45 degrees faster than light. And in that case, you have to reach a singularity. Another property of Schwarzschild black holes, which I didn't mention before, is if we look at the metric, beyond the Schwarzschild radius, the radial coordinate, the radial distance and the temporal distance switch signs. So it means that you have to an outside, you cannot see inside a black hole like we mentioned, but you basically have to move forward to the center. Like the radial distance always progresses or diminishes in that case, while the temporal doesn't have to change. Like like you don't have to move, but you always advance in time, so it switches. Like you don't have to advance in time, but you always must move to the center. So this diagram describes the collapse of Schwarzschild black hole. Anything else?
Yeah, so you can think of this Vaidya metric, which is basically, you can think of it as a sphere of light or photons, so that you'll have null geodesics, and it's collapsing at the speed of light. Someone's shown a flashlight, a spherical flashlight, and now the energy is crushing inwards. And if you're in the inside, then you're racing to get outside of the event horizon before the light sphere collapses closer than the event horizon. Because until the light sphere has reached r equals 2m, there's no black hole. There's not necessarily a black hole yet, right? I mean, the sun has mass. It has a Schwarzschild radius, but because the sun is so much bigger than its Schwarzschild radius, about 100,000 times bigger, there's no event horizon forms. There's not enough mass condensed into small enough space. If the sun were suddenly to implode and you were at the center, you would try to get out before the sun becomes smaller than its Schwarzschild radius, because when it does become smaller than the Schwarzschild radius, it is then too late, and you can never get out. That also means that if you're, for example, in this diagram, if you're sitting on the word event in this diagram, then it looks to you like you're in vacuum space-time. Everything is flat. There's no mass internal to your position. You don't even feel a gravitational field. You're in vacuum. But without knowing it, your future is inside a black hole, because you're already past or internal to the event horizon. You cannot cross your way out of it. So because this mass is falling from outside of you, and it will form a black hole, it will cross the event horizon in your future and external to your position. You won't even feel it happening, but you are already, without knowing it, inside the event horizon of a black hole, and your future is in the singularity.
Okay, so now we get to Penrose singularity. As I mentioned before, Kerr made a solution for rotating black hole in 1963. As you can see, the metric is very complicated, and you can see terms like sigma and delta and A. They're also like functions of all the coordinates, and there is a mix of because of the rotation, there is a mix between the time coordinate and the azimuthal coordinate, like the rotational coordinate in the last term in the metric. But it has, as mentioned in the historical context, like it has a singularity in a case of in a case where the spherical symmetry is broken. Kerr black hole have many interesting features. It actually has two horizons, and it drags space-time around it in a speed higher than the speed of light. After a certain distance, it's called the ergosphere, as you can see in the small figure above. What Penrose actually did is he generalized the collapse process described before for any kind of an array that collapses. So a short bit before Penrose came up with his singularity theorem, an Indian physicist named Rai Chowdhury, I think, came up with an equation that describes the change in the volume of a small ball of matter, where there are forces that cause it to, like the shear, and the shear is like basically creates changes it from a spherical object to an elliptical object, and vice versa. It's like and shear causes it to converge, while vorticity causes it to diverge, to explode. And as you can look at the equation, it has theta dot describes the change in the volume, and some of the terms are negative and some of the terms are positive. So in certain situations, Flick told me before, when there are no cosmological constants and specific conditions, you can see that ball of matter is bound to converge to a small region, small volume of space. Anything extra?
So there are two versions of the Rai-Chowdhury equation. One for what you call matter, so time-like geodesics, and one for photons, for light-like or null geodesics. They look. I think the only difference basically is maybe this 3 becomes a 2 or some numerical factor. But the point is that if you have some bundle, so if you have a group of geodesics, of light rays, for example, in a particular direction, then you know that if they're pointed inwards, they'll cross. If they're pointed outwards, they'll diverge. If they're parallel in flat space, they'll continue to be parallel. But now what gravity does, what matter does, is it acts as a lens, right? Gravitational lensing. And it would work to focus the light rays. So even if they started as parallel, or even slightly divergent, they'll now become more focused and eventually converge. If bending is strong enough, they'll eventually converge. So this theta, which is the expansion, is basically measuring whether the bundle increases in divergence or decreases in divergence. And we see that most of these terms are negative, and these last two terms come from the Einstein equation, from the field equation, which is related to the stress energy tensor, the content of space-time. And if the matter satisfies energy conditions, null energy condition, weak energy condition, strong energy condition, all sorts of things we expect normal matter to obey, relation between positive energy density or positive pressure, things like that, then these terms would also be negative, and expansion would be negative. So gravity in this case would focus the light rays, and if it focuses them enough, eventually they'll cross or meet at a point, which I guess is what leads us to your next slide.
Yeah. Eitan, I have a question before you go to the next one.
Okay.
What does the square brackets mean?
Ofek? There is like, I know it's basically a contraction of the Ricci tensor with the geodesics, but I don't have an intuition for it like that.
Okay.
Ofek, you wanna?
I don't remember this exact notation, what the E means and what the brackets mean. You have to look here both at the bundle itself, which is defined by the vector field X. And then you see on the right, you have the derivatives and covariant derivatives of the vector field, and this mixed term with E is probably some sort of relation of the energy density part of the stress energy tensor contracted somehow with the field itself, with the vector field.
Okay. So that leads us to Penrose singularity theorem, which Penrose described the term called Trapp surface, which is a two-dimensional closed manifold. It can be a sphere, it can be any smooth shape in a two-dimensional and 3D space you can imagine, smooth and closed, not like a paraboloid, but ellipsoid, for example. It has the property that all orthogonal light rays, all orthogonal geodesics at the surface converge in the future. An example, like a sphere inside the Schwarzschild black hole, is such an example, because nothing can escape the black hole. Of course, if you take the sphere and all the geodesics pointing inward will converge, but even the ones pointing outward will converge. That's like that's the paradox or mystery of black holes. And like I mentioned before, what he proved is that Trapp surfaces exist in curved black holes, and also in certain and they exist in black holes with perturbations. I always have a problem with this word, which means that even non-symmetrical and not rotating, not like processing or anything, will still have this black at this Trapp surfaces. And once they formed, when matter collapses, they cannot be unformed. They cannot dissolve. So the moment Trapp surfaces forms, matter collapses. Just review, there are like this. On the bottom side, you can see the Penrose diagram of general, not like a spherical symmetrical case, a general collapse of a star. which it's written like this is the surface of the star, and in the point in time and space where the surface of the star equals the Schwarzschild radius of the star, then a black hole is formed, which is singularity, pretty similar to what we saw before.
Eitan, are you there? You went black. Black and silent. Did you fall into a black hole, Eitan? Did we lose you? Are you now in the singularity? Okay, so I'll carry on instead of our late comrade Eitan. The thing about Penrose settling the debate and the reason he got the Nobel Prize eventually was really about this point of showing things that are generic. Like we said in hydrodynamics and in nonlinear PDEs, it's very hard to show things in a general way.
I had a network failure, but
yeah. We realized you fell into a black hole, so I just carried over.
Okay.
So it's hard to prove things generically, and so everybody was thought that all these singularities arise in the Schwarzschild metric, in the Weide metric, in the Kerr metric, even only in very, very symmetric cases, and it would be the symmetry that really creates the singularity in the center. There was a similar debate about gravitational waves with the opposite result. That is, Einstein in his famous rejected paper claiming that there are no gravitational waves. The reason he claimed that there were no gravitational waves was because he showed that space-time with waves would include a singularity, which he thought was not physical. And Robertson and others later showed him that the singularity was a result of his cylindrical symmetry, and the symmetry created it, the coordinates created it. But there was no physical singularity. So he thought the same about black holes, that it's just, okay, you take a system that's super, super extra symmetric, you'd get a singularity at the point of spherical symmetry. There's no surprise there. But there's no physics there either, because it's not a real system. Penrose showed that you don't need symmetry to get a singularity. Any generic or many generic distributions of matter under very, very light requirements. You just need that, that geodesic bundles don't expand because your space-time, your stress energy content is not weird matter. There's no negative energy density or things like that. Positive energy density would cause your geodesic bundle to converge, and then if you create some surface which is also quite generic, a surface that's just trapped, and you create that in GR quite easily, it would naturally and necessarily converge to a singularity. And when the singularity is formed from generic initial conditions, then you expect these black holes to be a very common feature in our universe. So there's still debate going on between people, especially now with the Nobel Prize, about whether this proof really, whether Penrose really proved that black holes were generic, or whether he only proved that once a trapped surface forms, the singularity would be generic. And really, the black hole is not the singularity. The black hole is the trapped surface, the event horizon. So maybe the people who proved that trapped surfaces are generic should have received the prize. And of course, people think that Roy Kerr deserves the prize, and he probably does, because his solution is the generic astrophysical black hole solution. We expect black holes in the universe to have spin. They won't all be completely stationary. But what Penrose did was a leap, in the sense that the objection people had to black holes really came from objections to the singularities. They thought that you can create many distributions of matter generically, but something would also always stop them from really collapsing into something that appeared non-physical, like a singularity. Similarly to hydrodynamics, you might expect viscosity to save you, right? We don't usually see fluids in a glass of water exploding. Physical fluids, eventually something happens to them. So they thought the same thing would happen with space-time. They thought singularities would not form, and then black holes are unnecessary because you don't need. If no singularity is forming, you don't need a black hole to surround it, and you don't need them. Penrose proved, and later with Hawking, that singularities can form generically, and then the black holes, which are the surfaces surrounding the singularities, or censoring them from us, so things don't come out of the singularity into our space-time, was called the cosmic censorship conjecture. Really takes the next step of saying that if singularities are generic, black holes are generic, and then it's just a matter of looking for them. And that, of course, is the second half of the Nobel Prize, the people who convincingly showed that a black hole exists at the center of our galaxy.
But Ofik,
yes,
why did he receive the Nobel Prize? The Nobel Prize are for like physical or experimental evidence, and not just any type of relation to some theory.
The Nobel Prize is awarded to great ideas which have been demonstrated experimentally or observationally.
But Penrose didn't talk about if there are black holes. He talked about something more specific, some property.
So as Eitan, if you go to the first slide, Penrose got the prize for the idea or the mathematical basis for the idea that black holes are a robust and generic result of general relativity. So our spacetime should produce black holes generically. It's not a mathematical curiosity. It's not some weird function that can't really be materialized. He theorized and explained why these black holes should actually generically form in the universe.
And all the others before him just said that it's a mathematical option, not more than that?
They solved Einstein's equation in vacuum, or in the Vaidya case, in a very particular matter distribution, a perfectly spherically symmetric sphere of light particles collapsing at once to a point. So they gave all these solutions which could be, mathematically they're sound, they could be a black hole, but one doesn't really expect any of them to ever appear in nature. You never expect to find a Schwarzschild black hole. You never expect to find a Vaidya black hole.
Okay.
Since the 70s and 80s, we know that we do expect to find Kerr black holes because they're stable to perturbations, and we understand the perturbative behavior of Kerr black holes. So we expect any black hole that forms eventually to asymptotically approximate a Kerr black hole. And that's part of the debate, by the way, about a Nobel Prize to Kerr. When can we say that we've seen a Kerr black hole, justifying a Nobel Prize to Kerr for deriving the idea or the solution of a Kerr black hole? And I think that now with the Event Horizon telescope, when they measure the spin of the black hole M87, I think that will justify a Nobel Prize to Roy Kerr himself. But Penrose got it, again, not because of the Kerr solution, not because of any particular Schwarzschild or Reisner-Nordstrom or Vaidya metric solution, but exactly for showing that you don't need a specific highly symmetric metric solution to form a black hole. That you would generally form a black hole from some collapsing star, and then once you measure a black hole which you think is a result of a collapsing star, that basically proves that it's a generic process that happens in nature, in the universe.
Yes.
I will add to that when I took my GR course, it can be shown that in a Schwarzschild metric, and correct me if I'm wrong, in Karen Rice or Nordstrom is the same. It takes you asymptotically infinite time to get to the event horizon if you're a point particle. So I asked this morning, I had like this, if no matter can fall to a black hole when you're an outside observer in infinite time, how can like a black hole form or expand? And I had a discussion with Ofik this morning, and we said that, let's say, even an electron falls into a black hole, the event horizon of the electron and the black hole together is bigger than the event horizon of the black hole. So you do cross the new event horizon in finite time, although it's like I'm just waving my hands, and basically the proof for this is much more complicated than what I just said, because you know that it's not a sphere, it's not symmetric. It's so I'm just saying that the Schwarzschild metric as a solution has like many like paradoxes. At least that's the way I thought about it back then. Like that nothing can reach the black hole, so what's the point of, like, it's just a gravitational force, but it has no physical plausibility.
There is no gravitational force.
The gravitational field.
Yes.
Gradients of the gravitational field, hereafter called the gravitational force.
I have another question, like partly related, at least to the presentation. You said before that you have no way to know that you cross the event horizon.
Right.
Like for you, it's the same thing, and you haven't noticed any change. So, as if you are an object that crossed the event horizon, so you can, like, you can say that everything in all our universe is capable to be inside like a black hole without knowing that, because there is no way to probe the situation.
That is correct. We could have all entered the black hole during this call and not know about it.
So, like, any inertial system, no, you must be in a part of non-inertial system to see an object that goes into a black hole, right?
What do you mean by seeing an object that goes into a black hole?
Because if there's some, if there's a, okay, if a particle, let's say a particle has personality, okay? If a particle is flying towards a black hole, he doesn't know that, right? Because he cannot tell the difference between before, after, or close to it or far from it. But
right.
me
so the Schwarzschild metric, like we said, the singularity in the horizon is only a coordinate singularity. Change coordinates, it goes away. It's a solution for vacuum, so there's no matter and there's no stress energy tensor, and the Ricci tensor is hence zero as well. The Ricci tensor and the Ricci scalar are zero. So basically, you don't feel anything particular when you cross the horizon. You can write a system of coordinates around your point. It's called Riemann normal coordinates, and your space-time area around you would be completely flat. It would appear to be completely flat, and you have the equivalence principle and all those stuff you learn in GR. You can do experiments around yourself, and everything looks completely normal to you and your small surrounding.
But isn't a stationary object, okay, in quotation marks, is the one that it's been accelerated, or the one that is not on some geodesic?
I don't know what you mean by stationary in this case. If you're in a spaceship and you're falling into a black hole, then you're free falling and you're an inertial observer in that sense, and you can do
but
experiments.
only external viewer can see that there's some spaceship falls into a black hole, right? Because the one inside the spaceship is in an inertial frame. He doesn't do anything. He's just sitting in place.
Right. Someone looking from very far away would see you becoming more and more dim and more red. You'd
Exactly.
be redshifted when you fall close to the horizon.
So that's why I'm saying.
Outside observer would see.
That's why I'm saying that you need to be in a non-inertial frame of reference in order to observe something relates to a black hole, like a particle falls inside the black hole, because the particle itself or the astronaut in the spaceship cannot tell that he's falling into a black hole. Only non-inertial observers can talk about black holes.
I don't know. If you're very, very far from a black hole, I don't think it would matter much if you slowly fall in or if you're just stationary outside. You would still see this redshift.
But by definition, if you're inside an inertial frame, you cannot see any indication for a black hole that affects you, at least.
If you and I circle a black hole, and so I'm on a geodesic, I'm on a closed geodesic very far away in a circular orbit, and so I'm free falling. I'm free falling. I'm an inertial observer, but I'm not free falling into the black hole. I'm free falling around the black hole. And then you jump into the black hole on a geodesic that's radial and leads inwards. And then I would see you redshifted and becoming dimmer, even though you're free falling and I'm free falling. But we're on different geodesics.
It depends if you're a massive observer, right?
Well, it's easier for me to do experiments if I have mass. But for example, if what you do is emit photons, and what I do is measure their frequency or color, then I will see your photons getting redder and redder the closer you fall into the black hole. And I'm free falling.
But isn't the difference? But the difference between the two objects, the one that is falling inside the black hole and the one that's only circling around, I think it's important one, because maybe the one that's circling around is free falling, but it doesn't have any trajectory that will be like into the black hole or be infected by a black hole or like.
Affected? Of course I'm affected by the black hole. If there were no black hole, I would not be circling it. I would be going in a straight line.
Yes, but I see a difference between the two interactions with the black hole, because one is changing your position relative. If we're talking about distance between the two objects, you always change your position, yes, but you'll never change your distance to the black hole, right? While the other one that falls straight into it does change. Not does it changes its position.
You can try to do the calculation, the redshift calculation, and take the Schwarzschild metric, write the equations for the two geodesics, mine and yours. They're trivial. Mine is circular and yours is radial. So it's an ODE. You don't even have to do a very difficult calculation.
Okay.
And then follow a photon coming from you out to me. Say every time I complete an orbit, I look at you and see what's going on with you. And I'll see you becoming redder and redder. This is actually an experiment that was performed on Earth. Of course, there's no event horizon on Earth, but like Eitan said, the Earth can be thought of from the outside of the mass of the Earth as a Schwarzschild metric, because it's almost spherically symmetric and it rotates very slowly, supposedly. Slowly enough for us, for our purposes. And what they did was they had planes, and we even do it with the GPS satellites. We can measure the discrepancy in the time that the satellites measure, because they're higher than the Earth's surface. So we on the Earth are deeper in the potential well of the Earth than the GPS satellites. So time ticks differently for us and for them. And that's a measurable effect. It's like 45 nanoseconds a day or something like that.
But the other point that I'm talking about is that you will never feel if you're in a closed spaceship and you're falling into the black hole or just circling around. In both cases, you won't be able to tell that you are experiencing anything. You're just free falling or floating inside your cabin, inside your ship.
Yes.
So okay, so both situations won't tell you that you're interacting with the black hole. You will need just a third observer that can see that one is circling around and one is falling. Because
yeah, so the event horizon is a global property. That's what the Vaidya metric shows us. It shows us that something in the large scale structure of space-time, that is the matter that's falling inwards, crosses its own event horizon and then its own Schwarzschild radius, and then an event horizon retroactively forms. So you can be within an event horizon even if the matter has not yet collapsed. It's just going to. It's teleological. You have to know the future to know where the event horizons are.
So in any case,
knowing the future is equivalent to having an observer infinitely far away, which can review all of the history of space-time.
Okay, so when I'm inside an inertial frame, I don't have any way to observe the future or something because there's nothing changes. You're the most dead person that is able to.
It doesn't matter if you're an inertial frame or not, right? In GR, any frame is for that purpose. In any frame, you can only measure your own causal past, the light cone behind you, with all the curvature included, but your own causal past. If you're in the infinite future, your causal past would include a lot of the universe's history. Of course, it would not include anything that happens inside a black hole.
Okay, so
anything in a black hole is now causally disconnected from future infinity, because its future is not infinitely far away, it's the singularity, right? The future of space-time is no longer connected. It's infinity plus all the black hole singularities. And each of us will end in one of those endpoints of the universe, either at I plus infinity, time like infinity, or in a singularity of a black hole.
So bottom line, I cannot talk about a black hole that I'm being interacted with. I can only talk about interaction of some other object with a black hole.
I don't know what you mean by interacted with. We can measure the Earth's gravity quite well.
Okay, maybe I need to think about it and much better compose my questions. I don't know. But it's still not so clear to me. I don't know why.
Any other questions?
Yeah, I'll ask, actually. Regarding very similar to what Max asked, is it physically, like there are tidal forces when you approach the event horizon of black hole?
Yes.
How strong are they in the black holes that we observe, like the supermassive ones and the massive ones? Like, is it plausible to cross the event horizon with a spaceship without being torn apart?
Okay, so that's actually you can do the calculation in GR, and you can do the calculation in Newtonian mechanics, and the answers are not very different. So let's do it in Newtonian mechanics. You take a mass m, and then you know that the gravitational force. What? Something happened?
The blackboard option, it helps.
Blackboard option.
I think like in share screen, you can, whiteboard. Share screen, whiteboard.
Share screen, whiteboard. Share. But Can everyone see this?
No, I don't see anything.
Now, do you see a whiteboard?
No, we see you frozen in time.
Ah, now I see my board.
Okay. Does everybody agree with this?
No, you need to put another mass.
Another what?
Another mass in the equation.
Okay. Okay. This. So just to ignore the other math, let's put the acceleration that you experience is gm over r squared. Now, for a Schwarzschild black hole, the event horizon is at r equals 2gm over c squared. So we'll plug this in together and we get a equals gm divided by 2gm over c squared. And now we open it up, and because I didn't use g equals c equals 1, it's going to be ugly. There's 1 over g. There's a crucial 1 over m, because I have 2 m's in the bottom and 1 on the top. I have 4 c's on top, and there's a factor of 4 in the bottom. Okay? I do not commit to the numerical factors g4 or c to the 4th. You can check me with dimensional units to make sure that it's correct or not. It doesn't matter. The important part, of course, is that it goes like 1 over n. This is saying that the gravitational acceleration that you feel, which in GR we know is a tidal acceleration. It's really the difference between two geodesics headed towards an object. So if they're separated slightly in space, they'll fall in slightly different directions. So if they're slightly separated in space, they'll fall in slightly different directions and they'll get closer in space. So the acceleration they feel towards each other is really a tidal acceleration. And here we see it goes like 1 over m. That means that the bigger the black hole, the more massive the black hole, the smaller the acceleration. And you can plug in the units and see that if you're talking about a black hole like the stellar mass black holes that we see with LIGO, maybe 10 to 100 solar masses, you get quite a heavy, quite a strong force, or high acceleration. Those things are painful to fall into. If, on the other hand, you take a supermassive black hole like the one at the center of the Milky Way, which is 4 million solar masses, or something like the one that the Event Horizon Telescope photographed, radiographed in M87, which is 1 billion solar masses, the acceleration is a million or 1 billion times smaller, and it's actually quite weak. It can be much weaker than the acceleration of the Earth, for example. So it's actually not that bad. You can kind of slide into a supermassive black hole, you know, like butter.
But isn't that contradictory to the idea that you won't know in any way that you are entering a black hole?
Well, it's not happening because you entered the black hole, right? Okay, I used the Schwarzschild radius here to ask where you feel the force, but you will feel it a little outside and a little inside as well. This is just the typical scale of the force that you would measure in your laboratory on a spaceship around the black hole and entering into it.
Okay, you just won't be able to tell that you're past the event horizon or not.
Right. You could, in a sense, spend years and years measuring the exact mass of a black hole from the orbits of particles around it. Then when you know the exact mass, you could take a spaceship, fall into the black hole, all the time ticking a pendulum clock and measure the frequency of the pendulum. And you know the frequency of the pendulum is related to the gravitational acceleration g, right? It's a square root of
Yeah.
g over L.
Yeah.
And when you measure the frequency of the pendulum to be the exact acceleration you expect for the black hole event horizon, for the mass which you measured ahead of time, then you would know at this point I entered the black hole horizon. That's of course a very non-local, non-trivial measurement, but in a sense, you could do that to infer when you entered the black hole.
Okay.
Brings me to, if you finished, I have another question. You mentioned before that when we talked, and I know this from GR courses, that when you're inside the black hole, you don't get information from objects that fell just before you or that crossed the event horizon before you. You can't see them. So let's say you enter in a spaceship. The stern of the spaceship, the head of the spaceship is going before you inside the event horizon. And then you cross the event horizon. What would you see? Like you would see like how the head of the spaceship was before it crossed the event horizon. Like what? Just take two particles that have consciousness. One fell to the black hole before the other.
He's asking if the first one will say, "Hi, I have been waiting for you."
Like, why can't you notice this? That's why.
He won't. It will be like looking in your future, right? It will be if you jump with your feet down into a black hole, your feet will be further in the black hole than your head, which in the black hole sense means that they are in your future. And you cannot see into your future, right? You can only look backwards. So you won't see your feet again. I'm sorry.
So you can notice when you cross into a black hole, or at least when your feet have crossed into a black hole.
The problem is you might lose sight of them a bit before. They'll be redshifted before you lose sight of them, right?
Yeah. Ah. So you do notice something is happening.
Yeah, well, of course. When you get closer and closer, you'll feel gravity growing. It won't be much, but you can feel it growing. You'll see things outside as getting bluer and bluer relative to you.
So how is it? Doesn't it contradicts what the answer you gave to Max? Just
because you have to distinguish between local and non-local measurements. The equivalence principle talks about, and GR in general talks about local coordinates frames in space-time. Things are always locally flat. When does locality break down? When the length scale of effects around you become comparable to the length scale of your system. So, if your measuring apparatus is as big as the black hole, you'll be able to measure that it's in there, right? Your right hand will be the right side of your planet will be attracted leftwards, and the left side of your planet will be attracted rightwards if you're taking a planet and getting it close to a black hole. So people on the planet will be able to know there's something there, right? We know the sun. We live in the Schwarzschild metric of the sun. We are very much aware of its position and its mass and its effects. If your system is smaller than the typical scale of the background metric, then you are not aware of the background metric. You're in effect in the geodesic of the background metric. So all of these questions of, circle the black hole a few times to measure its mass, compare your different parts of your space station, look towards stars infinitely far away and compare what they look like before and after. All of these things are introducing very, very large length scales into your measuring apparatus. And in that case, you're breaking the equivalence principle because you're breaking the geodesic assumption. You're no longer a point-like measuring system. So now you have to follow the geodesics of all the different parts of your system and compare them to each other. You're actually now performing a large scale or global measurement rather than a local measurement.
Yeah,
Okay.
but like human's body compared to a massive black hole and like very small scale, I'm saying, like it's not like
You'd have to check if the time that it actually takes your body to, from feet to head, to cross into the black hole is not much or much lower or out of the same order of the time it would take you to see and analyze your feet going red and disappearing.
and to get into the singularity, whatever.
A singularity would take, I think I calculated it once, and it takes about a minute until you get to the singularity once you're inside. Depends on the mass, of course. Max?
Yeah. So can I say that I can produce the same effect with some massive object or with the right mass, let's say like that? I can get the same effect like feelings wise, okay, stretching and the gravitational pull and how it affects me. I can get the same situation without a black hole, but I cannot differentiate between if it's just an object or a black hole.
So we need two things here. We need the gravitational force, and we need the tidal force as a derivative of the gravitational force.
Yeah.
So the Earth pulls on us stronger than a supermassive black hole at its horizon. But tidal force-wise introduces another factor of R. So again, you have to divide by the R of the black hole. And for a black hole, the R is, by definition, the smallest possible for an object of that mass. Right? Because if it were any smaller, it would have been in the black hole. That's the Hooke conjecture. So you can emulate one, but you can't emulate both. You can emulate the gravitational force, but if you want to emulate both the force and the so both the force you would feel and the tidal force you would feel, how crushed or stretched you would be, you'd need to be as compact as a black hole.
But in essence, if we would just disregard the event horizon, there is nothing different between a black hole and just a regular mass. Okay, then a regular object with mass.
Not really.
So
in classical GR, if you're outside some mass or outside the event horizon, there's actually a theorem that says that the only solution to vacuum space-time in static spherical symmetry is the Schwarzschild solution. So if you can approximate your space-time as static and spherical symmetric enough around a mass, it looks like it's a black hole, right? If the sun were to suddenly collapse into a black hole, the Earth would continue on its present orbit as it has for billions of years.
Yes. Okay. You just won't get because there is no event horizon. You won't have any place for questions like all the paradoxes and stuff.
Yeah, it would, and you don't get light, things like that. But gravitationally, it's the same. Gravity doesn't really care what you are.
Okay, so still you cannot know if you're falling into a black hole or not. You can know that you're interacting with something that is gravity or mass related, but you cannot
measure the mass. You can measure the mass and you can measure the spin.
Yeah, but you have no idea what is the classification of the object that you're interacting with. Like
no, not without measuring higher multiples and doing non-local measurements and more complicated things. This, by the way, is part of the problem, and of course, proving something is a black hole. Right? We started by saying observing a black hole. What does that mean? You can observe a mass. Sometimes you can observe a spin. Above that, it's hard to say if you're measuring a supermassive compact object, which is what the Nobel Committee cites Gez and Genzel as doing, a supermassive compact object. They can't say it's a black hole because it's really hard to prove something is a black hole when you cannot see it. All you see is the mass effects, and everything has a mass. That's part of what we do in gravitational waves, right? We try to measure the perturbations of a black hole in multiple modes, maybe probe the horizon a bit closer to be able to claim, okay, this, it's not just the mass of a black hole, it also vibrates like a black hole. It has a horizon that looks like a black hole. But it's much harder to do because you have to probe deeper and deeper, and use more complicated physics of perturbations of the thing that you're measuring. Because if it's static, you cannot measure it anymore, or at least you cannot differentiate it anymore. Okay, we're already way over time, but we did cover like 60 years of history of black holes in that time. So we'll finish now. I'll put the recording on when it's ready. We'll have a pre-semester group meeting on Wednesday. If anyone has plans for the semester he wants to share. And other than that, next week, like I said, we start the full schedule with seminars. We have lots of seminars this semester. And good luck to all of you. It'll be an interesting semester on Zoom and stuff for everyone. So good luck.
Thank you.
Thank you.
Bye-bye.
Thanks.